So, okay, let's get started. I ask you guys to watch the recorded videos related to time series analysis or time series data set and recurrent neural net or LSTMs. So I'm gonna quickly review or recap what you guys learned. So the biggest the difference was that so far was if you remember, regression classifications, dimensional regression, so far is based on the snapshot type data or informations. Based on what you got, you have to make some kind of decisions or make estimations or predictions. But as you can see, the example that I showed is the sequence. In many cases, we have many systems or applications or data set that has a sequence matters. So we have to take the sequence into account, right? So that's why that was kind of the motivations. And the sequence means what is the sequence? You're gonna see bunch of examples around all the aspect, like speech waveforms and vibrations and medical signals, whatever. Even like weather forecast as well. So in most of real world data set is related to or in a form of time series data. So that's why it's really important to understand what's the mechanism behind. So I mentioned several times we can see the time series data in deterministic perspective or stochastic perspective. We have uncertainties or noise on it. And under the stochastic time series data set, we can think about stationary or non-stationaries. In non-stationary, we have linear trend or nonlinear trend, either exponentials or polynomial, whatever. And another key characteristic is you have periodic, or we call it seasonal trend. And in many cases, you assume that your models can deal with linear trend, nonlinear trend, seasonalities, and rest of them gonna be either uncertainties or noise that we are not able to describe. So that's U of t is gonna be like Gaussian distribution. And let me see. So here, probably like Markov chain or Markov process, some of them see that those Markov process has nothing to do with time series data set, but I believe that is because later on what I'm going to explain is that hidden Markov models. That's why I want to explain the Markov process a little bit. And so maybe if you're from like industrial engineering department, probably you heard Markov channel process before, but most of them probably, I guess, it will be the first time. So let me see. This Markov process is some kind of, how do I say, like it's modeled the sequential data set. So we're gonna consider or think about the systems that occupy one of n discrete state or class or categories. So suppose we have n different states. We don't know what it is. It doesn't matter. If you have two, it's binary classes, so you can think of it as a binary classification problems as well. But in general, we're going to have n different and discrete state. Okay? And our system is going to occupy one of them. Okay? Now let's think about the sequence. Now let's see, in time index, these are the time index from 0 to 1 to up to time capital T. So these are the sequence that I observed or that I got. I want to calculate or compute the probability of that. I mean, if some of them I know that is not familiar, some of them are not familiar with the probability concept, that's totally fine. Don't worry about it. And the probability that we're gonna have that such a sequence is equal to, at the first time, we're gonna have Q of naught, step probability, and next time index represent the conditional probabilities. So in the first time we got that Q of naught, given that we have to have Q of 1. That's a problem. So we are here, and the probability that I'm going to get Q of 2 at time instant 2 is that we have previous sequence. Given that condition, we have to have Q of 2 at time t. So that's another conditional probabilities. And that's another conditional probabilities. We have to multiply all of them. Okay? So in probabilities, we can say any joint distributions, the joint distributions can be factored into the series of conditional probabilities. That's what I'm going to do. But the issue is, this is in conceptual or theoretically that's correct, but in practice, it's almost impossible to compute the conditional probabilities. It's extremely difficult. That's why the Russian mathematicians, Markov, he came up with the good assumptions. What kind of assumption they have is that, suppose we have that kind of conditional probabilities, given all the previous sequence, given that, that's the probability that we're going to observe Q of t plus 1. So he's going to make kind of big assumptions is equal to. So we say, let me see. So current time, suppose at t. So in the near future, so t plus 1, all the previous up to t minus 1. So if we made this kind of assumptions, that means that in order to predict the future, all the information that we need is current. We don't need the previous or past informations or data or sequence. I mean, in most process or systems, that's not the true, but somehow he's going to make such kind of assumptions. It might be different from the true process, but that's totally fine because he just made such kind of assumptions. Another way you can say it is information state is sufficient statistics of the history. Okay, I will explain. So now in joint distributions, this one, the sequence that we have been observed, so we can write it in that way. That's always true in theory. But under the Markovian process assumptions or Markovian property, right, we can ignore these two. So always like that, we can simplify the conditional probabilities. We can simplify. That's the only reason that Markov made such kind of assumptions. It might be different from the true, like what's happening in the real world, right? But that's okay because anyway, we're not gonna able to compute the joint probabilities. So future is independent of the past, right, given present. That's what Markovian property says. What kind of example that you guys can think of? Suppose we got rain, and next day snow, and next day sunny, and another day sunny, rain, and snow. That was all the track record that we have related to weather forecast. And I want to ask you, what's going to happen tomorrow? Okay? And from like historical data set, probably we are able to compute some kind of probability. That's fine. But to simplify the problems, if we apply the Markovian properties, all these, it's waste. We don't need that. Only thing is that we got snow yesterday. Okay? Or I would say we got snow today. And I want to predict the weather of tomorrow. That's the concept of Markovian properties. The only reason is that in order to make the computation simpler. Right? And in order to define Markov chain or Markov process, at the first time is that we need to define n discrete state. And next thing that we need is a state transition matrix. State transition probability. Let me see, what's the state transition matrix P. So it's defined by like this. So now we are at state S. I'm going to make transition to S prime. And these are the state transition probability. We have to define it somehow. Don't worry about how we compute this state transition probability. In many cases, it's going to be given. So, since we have n different states, so from state 1, state 2, state n, to state 1 and state 2 and state n. So we're going to have n by n matrix. And each element have state transition probability as the element of that matrix. That's the key ingredient to define the Markov chain or Markov process. Okay? So the first thing is n discrete state, and next one is state transition matrix or state transition probability matrix. So I'm going to show you the one of the examples here. How many states? We have three discrete state, S of 1, S of 2, S of 3. We don't know what it is. It doesn't matter at this moment. And say you have S of 1 and S of 2, S of 3, three different states. And if suppose we are here at S of 1, that means that it's gonna make state transitions to S of 3 with probability of 1. So suppose we are at here, in next time index, I'm gonna add state S of 3 for sure. Now I'm here, and this said that I have two chances to transit to S of 1 or either S of 1 or S of 2. We have different probability assigned. Okay? So I'm here. In next time index, I might be in S of 1, the state transition probability of that event occur is like 1/3. And that's another case. Now, say I decide to change it this way. Now I return to S of 1, and then next times index, we're going to make another transitions. And then in this case, we can transit to S of 2. In S of 2, we have two ways of transiting. The first one is we can make it to S of 1 with the probability of half, or I can stay where I were, which is S of 2. We can stay at the same state as well. That's kind of the dynamic behaviors that we can describe using such kind of Markov process. And in this case, so this is state transition matrix. Let's see. From S of 1 and S of 1, S of 1, S of 2, S of 1, or S of 3, right? We have 0 probability, and we have probability of 1. So that's another way that we can represent in mathematical way. In this case, we happen to use matrix form. Okay. The reason why I want to explain Markov chain, when you talk about the time series data set, is that we can generate sequence from Markov chain. What do you mean by that? Let's see. Say I'm in S of 1, and I'm gonna just take the random process or transitions based on the probabilities. So I'm starting from S of 1. I might have chance to, I have for sure, like here. Now I'm transiting to S of 2, and as I'm stay there and make another transition to S of 1, things like that. So we are able to generate the sequence based on this Markov chain. Okay. If we take another, now I'm going to try another one, then the sequence being generated from the Markov chain might be different. So we call it this one is sample episode starting from S of 1. This is another sample episode starting from S of 1. So we can have infinite number of different time series data set. Okay, so again, I can generate stochastic sequence out of Markov chain. So, here we have tons of different theories or discussions that we can have under the Markov chain of process, but I'm going to skip all of them. Now I want to move on to another extension, which is hidden Markov models. So the only reason is, I'm not interested in introducing the hidden Markov models to you guys, but there is some key concept which is related to recurrent neural net. So that's the reason that I want to share the idea of hidden Markov models with you guys here. So in Markov models, I introduced the concept of state. State, what kind of? Alright, so let me say, I want to describe, I want to take some examples of me. Say, I want to describe my condition of health using the Markov process. So what kind of state I can define? Maybe I'm in good conditions, or I'm in bad conditions, right? You can have like two discrete states, or you can have more than that. So say these are the state Suppose I'm just make some assumptions that I have only 3 different states to describe the condition of health. Okay? But condition of health, that's kind of the conceptual definitions. Okay? That's the state representations. But the problem is, in many cases, the definition of the state it's a conceptual or abstract. So only thing is that we have a bunch of sensors, right, to get some kind of data set. So these are state, or say these are the state. Now we can measure like what kind of measures, like temperature. That's the observations, or pressures. That's like blood pressures, and what else? We have bunch of different sensors or data sets to like medically related like readings. Okay, those are the value reading the measured data set depends on the state, depends on the condition of my health. Okay, so we have some kind of observations. Have another observations. It could be like 2 and 3, and maybe this one is like say 1 and 2, things like that. So what I explained so far is that we have some kind of abstract state, we can define it, but in many cases we are not able to directly the sensors or measure that kind of state. But good thing is that we have some related observations, which is here is Y. Y is depends on S. Y is only depends on S, the state. Now with that baseline where we have, now I want to add some kind of dynamics on it. Now the condition of my health, suppose I'm right now I'm good, but tomorrow nobody knows, right? And yesterday we don't know. So you have some kind of dynamic on the state. That's why I want to describe the sequence of state using Markov chain. But observation is not. Observation is different from state. The observation is only related to or depends on the state. That's kind of another assumptions or another way of another perspective of looking at the dynamical systems. So assumption is that we can observe something that is affected by the true state. And I guess it's a natural way of thinking. So the problems or goal of hidden Markov model is that because nobody knows state, and only thing that we have is a sequence of observations, sequence of sensor readings, all related to Y. And based on those sequence of observations, we want to estimate what's the state of myself, or what's the current state of the system. That's and on compute the probability of that. That's another condition of probabilities. But like I said, this one is different from That's different from Markov. These are we made condition on the state, but here the Markov process is we made a condition on the observation, sequence of observations. Based on those, or given the sequence of observation, I want to estimate the probability of the current system being at state of S. I want to estimate we want to compute the probability of the current state. Okay. That's I'm not going to explain how you compute this. I want to introduce only the purpose that I want to introduce the concept or the way they're looking at the way the hidden Markov model looking at the systems, dynamic systems. Again, state and observations, we have dynamics on it. Another thing, personally, I believe that is the recurrent neural net is heavily related to Kalman, the concept of Kalman filters. I have only 2 slides for related, so don't worry about it. If new at the Kalman filters, that's totally fine. Again, here we have, now I use a different notations. In the previous one was S was state and Y is observations. But in the society of Kalman filters, the state is X and the observation is Z. That's the way their notations. So that's a state, and this I will say observations. So again, we have dynamic sequence of states, and the observation is only function of state, like that. Now, the idea of Kalman filter is that suppose I know the state in the previous time index. I want to know the current state. If we know this guy, I want to predict. If that's the only thing, that's the same as the that's same as Markov process. But the good thing is, we have another data or another information, which is I do have sensor readings, or I do have observations at current time of t. So somehow I want to combine the previous state and current observations to have better prediction on what's the current state. That's the Kalman filters. Of course, we have made a lot of assumptions on that. We have to define, let me see, related to linear or Gaussian, linear state space representation with the Gaussian distributions, things like that. We have many assumptions on it. But again, it's totally fine because we're not gonna talk about the math. The only thing is concern is that what's the assumption that they have to describe the dynamic systems. I mean, if I'm doing that, it's not easy to understand. So I'm going to show you another movie clip. Let's see.
There's a really nice little graphical illustration of tracking with the Kalman filters. So let's suppose we have some current estimate of where we think things are, right? And that's what's represented by this little circle here in the XY plane. Our prediction shifts and grows, and that's why the size, if you look, you knew this as being.
Suppose at the prior time, we're looking at some, I would say, some object. So was here. And I want to estimate where that object is going to be located in the next, in the same size, but we have a lot of, basically what we're going to do, we're going to predict future, right? So we have large uncertainties. That's the way they have. They have larger circles.
A single, say, some number of standard deviations of uncertainty. So our uncertainty matrix got significantly bigger, and the mean may get shifted as well also. So that's our prediction. We then take a measurement, and you'll notice that the measurement here is offset a little bit. I mean,
Oops, sorry.
There's a really nice little graphical illustration here.
Now, with that, the predictions based on the previous state, now at time t, we made measurement or observations right here. So we need to somehow combine these two. Okay? These two, I would say data or information.
Offset a little bit. I mean, its mean is right in the middle, and it's actually tighter. So it actually has a tighter covariance than the prediction. Okay? But the thing that's important to realize is the correction has a tighter covariance than either one of them.
So what Kalman filter says that if you have these two informations, the more accurate prediction is right here. So that's kind of the best prediction that we can make based on all the information that we have. What kind of information is? We have observations or measurement, and we have predictions from previous state. How do you make these? We need a lot of math, but I'm going to skip. Okay, that's the idea of Kalman filters. So with that, I want to move on to, let me see. Recurrent neural net, which is gonna the recurrent neural net. It's kind of the networks, the architectures can deal with time series data. Again, the same motivation here, sequence mirrors. Let me skip. Okay, let's see. So now, I'm sorry, but I use another notation here. I mean, Y is, say, observations, and O is kind of output. And you can think of as a classification as one of the examples here. Suppose we have sequence of observations, and based on that, with that data set, some kind of sequence, we have to make, whether say this belongs to class 1 or belongs to class 2, things like that. It's a class. Think of it as a classification problems. And from here, I made this means that here classification based on the input, right? And with that, the only difference is that we have input and define the latent space. We can use a PCA or autoencoder or whatever. The same as the concept of a state in hidden Markov models or Kalman filter. And this is sensor readings or in this case is input or observations. And the classification that we're going to make it is not based on the input. I'm going to do something based on the state. Now that's kind of more enhanced, right? Another thing is that, again, even though this is the sequential data set, I'm going to make another classifications. Because here I didn't take the historical data set or the sequence into account. to make better classifications. Okay, now we have to take the idea that we have to take the fact that we are dealing with sequential data set. So let me show you. So that's another modification that we can make. We have some dynamics along the latent state. That's the model that we have. We're not going to have dynamics on the observations because the assumption that we have is this is true dynamics and this one is the observation is the output of or depends on the state. So dynamic is not, what I'm saying is that I'm not going to do this. I'm going to do that. Does it make sense? Again, without this one is same as hidden Markov process, right? Hidden Markov models. State, we have dynamics on it, and these are the observations. Some kind of sensor readings or measurement. And if this is happen to be classification problems, we have to make what kind of class on it is depends on the observation, depends on the state, because that kind of contains the true information. So that's a state. Okay. So what we're going to do, based on the input or observations, we have to estimate state, right? We have to estimate state, and we have to estimate state dynamics. And based on that, we have to make decision on which class on it. So that's the idea of, or structure or architecture of RNN, which is Recurrent Neural Net. Here, hidden state extractions and transformations, good for sequential data, dynamic behavior, things like that. So let's move on to another one. So now I'm going to, okay. So that's the, say now we're dealing with a sequential data set. Let's say this is X or Y? Let me see. X. Say this is X1, X of 2, things like that. This is same as ANN in neurons. Now this is input layer and hidden layers. Another hidden layers. Now it's output. That's just same as ANN structure. ANN structure. You have sequential data set, column vector, and only thing is that we can make neurons. Is that right? Input and first hidden layers and second hidden layers and output. Now, what I want you guys to see is instead of looking at this way, look at that way, then we can represent like this. So, I mean, this is kind of notation between you and in this course. So, single neuron represent like circles, and if you look at this one, that means this is not a single neuron. We have a sequence of neurons. So looking at this way. And I mean, this kind of another representations. And the input at each time, a vector, and each layer has many neurons. Okay. Suppose we have another, let me see. So we have this kind of the sequential data set. And let me see how many. It's 8. And we have 8 like data points. And that, another 8 data points like that. In this way, you can do that. You see what I'm doing it? So we're gonna take 8 of them and put it here. And another 8 data points, put it here. Is it? Yeah. And if I want to do, so this is first hidden layers, I want to take, without this, I'm going to only take 8 different points, sequential data points. Having that means I have 16 data points into consideration. But this is not a correct way because this one's better. Because we're going to assume that all the dynamic behaviors we're going to define not in the input, we're going to define the dynamic behaviors using this hidden state, hidden layers. So this is correct way. You see that? Now I'm going to use such a notations. So if you have that, that means we have many data points in this way. Okay. We have chunk of data points. So we suppose we have 8 data points. That means we have 32 data points into considerations. I'm going to take 32 previous or historical data set to make some kind of decisions at the end. Okay. I'm going to sliding the predictors because assume that only 32, that means including the current state. So we're not going to these going to fade away. I'm going to shift it. So sliding predictors, we're looking at the last few data points or days or data points. Since this is a like finite number of data points in sequence, we call it finite response systems. Something that happens today only affects the output of the system for n days in the future. N is the width of the systems. But the issue is that if we increase the history, make the network more complex. I want to do that. Somehow, I mean, in engineering sense, the finite response model is good enough, right? So in order to predict the weather of tomorrow, probably I would say a week or a month, that's good enough. But the problem is if you take more than that into consideration. If we increase the historical data set or informations to make better information. We believe that if we have more data set, we can make better predictions or accuracy. But the issue is that we end up having more complicated or complex networks. And in theory, we can go infinite. We can go infinite, like this. In theory, it's not practical at all, but you can think of it. Hey, I want to consider all the data points. But as you can see, in many engineering systems, and probably with weaker and weaker influence, if it's far away from at time t, in the current time, the weights that we can estimate it gets smaller and smaller. Eventually, it's gonna make no influence at all. In theory, we won't have infinite memories, but it's impossible. So that's kind of issue that we have. So, like, brilliant previous researcher made come up with a good idea. So again, still, I do have infinite response systems. So to say this is output and these are the inputs. Again, we have infinite data points. These are all of my inputs, and we thus take all the historical data set with the infinite time span. I don't know what it is, but suppose we have some kind of functions to predict, which is totally fine in theory. But in practice, it's impossible because we have to have infinite memories to memorize all of them. But again, here, let's see. In order to predict y of t, I need, of course, x of t. And what is this? Y of t minus 1. And y of t minus 1 is function of x t minus 1 and y of t minus 2. And this guy is function of x t minus 2, y t minus 3. So in y of t minus 1 contains all the x's values. The good thing is, it requires only 2 memories instead of infinite, which is good. So in order to predict y of t, we need to know, or we need to estimate it, y of t minus 1 and x of t. These are the same. Again, just writing this way, only thing is 2 memories, but the output contains information about the entire past. That's the idea. That's a brilliant idea, actually. So remember, with that idea, we call it autoregressive. Just remember that. Autoregressive. How to implement it? Okay, so let me see. Now we do have here x and state and predict y, but we have to take the previous y into account. Now I'm moving back like this. Now we can implement infinite response, let me see, what's the infinite response systems with a finite number of memories. You see that? So that's how we implement it. But here, something that we don't like it is that, let me see, using this one, let me write it, erase these things. Here we do have output and inputs. But remember, in hidden Markov models or Markov chain or hidden Markov models, Kalman filters, we define the concept of state. And hoping that the Y here is the output of state. So I want to induce the concept of state into infinite response systems. Okay, so alternative models for infinite response systems. Now we do have, now again, it's a different notations, because if different communities have preference on using different notations here. So let me see, here in this X is input, H is state, and Y is the output. This is same as the autoregressive. The only thing is that we replace H of t. We replace Y of t to H of t. Here in H represent the state. So we have dynamics along the state, not the output. And the output is only function of state. Okay, how we represent it? We can represent that way. So let me show you that. If you have one hidden layers, two hidden layers, okay? So the only difference is that, I'm going to show you that one. That's using the output. This is okay, this one will be, this is the assumption that we have. We believe that dynamics is along the output. Here, dynamics along the state. Okay. So again, this is the final architecture with state determined by the input and the state at the previous time index. That's the now for the version of RNN, what do you mean by that is that, okay, if you have, so this is time, we have time index right there, and looks like we have many different networks, right? But actually we do have only single like that one, because we have memory in it. So we memorize at the current state, and we have, suppose we have new inputs, and we do have state values in the memory, and the data in the inputs, we combine, we update it. We updated that the value is on that memory. So these, if you draw like this, all the states or memories that look like it's totally different, but actually we can represent or implement these structures like this. Because what do you mean by that is that remember, like when you program it, we can just update the value of H. That's why we call it, let me see, where is recurrent? It's recurrent. That's what the RNN or recurrent neural net named after. So that's the basic idea of recurrent neural net, or RNN. It could be baseline models to deal with any sequential data. What kind of application do we have? Machine translation, speech recognition, text-to-speech, image captioning, video, or whatever, captioning, or understanding, whatever. Okay, so that's all kind of the explain. I complete all the explanation that I have. That's same thing. I'm going to repeat it with another representations. And suppose we have all the time series data set. We do have hidden state, and we're going to make some kind of decisions based on that hidden state. And at next time index, we received another input, which is time sequence as well. And we're going to update it hidden state, but we're going to update it having two informations from having the two channels of informations, one from the current observation at the current time, another information is from previous state. We're going to do something, updated age. And with that age, we're going to make another decision. It could be regression, it could be classifications, it doesn't matter. Right? Repeat it, that process. Again, these age looks different, but same. Okay? Because if we're here, let me see. If we're here, we don't need this guy, because we use that information to update age, so we don't need. So at this moment, we need only memories for age of 2. We memorize it, using that to update it. Now we don't need this one, so we're gonna overriding things. So that's why this is the only thing that we need. Again, there's another way they say this is, again, it's recurrent. Here, can you remember like ANN structures, we have weights and bias, and CNN structures, we define the kernels and all the elements inside the kernels we have to learn from the data set. Okay? In RNN structures, that's where we have all the unknown parameters. Most of them are matrix. And those are the unknown parameters. We have to learn those parameters from data set and time series data set. Right? But in the detailed stuff, don't worry about it, because we're gonna set up the problems and ask a keras or TensorFlow to estimate or predict all the weights and bias for us. Okay. But in general, compared to, ANN and CNN is much lighter models. If you remember, like CNN is much better, it's sparse. Right? But the RNN, a lot of unknown parameters that we need to estimate. It really depends on the length of the sequence that we're going to consider it. So it's not easy to train. It's not easy to train. So maybe it's like the performance is not like as good as ANN or CNN. Okay. Another thing is the RNN was good. It's conceptually it's good to start, because it give us opportunity to think about like the concept of a state or dynamic behaviors and things like that. But this actually, I mentioned that is that if this this, because we have many unknown parameters, it's not easy to train or learn the estimate all the parameters from the data set. And there's another issue is that since we talking about time series data set, we do have some kind of again we have to use back propagations to train. So we have to compute the gradient, and as we have longer sequence, we have vanishing or exploding the gradient behaviors. We have the similar issues here. So that's why people come up with LSTM, which is like more advanced than the RNN structures. So name is long short-term memories. Here, I got the example from like natural language process. Like I grew up in France. I speak fluent French. So let me show you. The idea is that here, okay. So in most mechanical systems, if this is time, now I'm here. And we do have all historical data. If that's any engineering systems, we're gonna have such kind of like influence to estimate the current values. Because if it's far away from where I'm at, it's gonna have less influence on it. That's kind of natural way of thinking for most engineering systems, but in natural language process, it's not. Okay. So somehow we have to keep informations like far away. So that's why in most the natural language processing, the vanishing effect is kind of big issues. I mean, I'm not gonna go in the LSTM into details. So you have memory cells and set of gating units. You have memory cells and forgettings, gating, and input gates and output gates, things like that. What's gating? Gating is that, so it's if you do element by element additions, we do that. If we do element by element multiplications, we can do that. Okay. And suppose we have signals, and we do have gatings. For gatings, the value is from always range to 0 to 1. Because you just take the sigmoid in it, so it's not difficult to implement. And if we do the multiplications, we can get it. That means that suppose we have 3 different values into our signal, and these are the gate. And if you have 1, that means we just passing through the values into next. So we got same. And if you have zeros at the gate, that means even though its input is 5, the output is going to be 0. So we're gonna not allow the values going through the gate. And if that's like half, that means the only half of information is gonna go through that gate. So it's like on and off, it's switching. So what we want to do is, what the LSTM is that we want to learn what the gate. So the idea is that, so these are the gate. So if the gate is, this one is blocked and this is open. So Like if that's that means that I can pass all the information through that way, in this way. So in LSTM, we're trying to learn the gating from the sequential data set. And these are the another animations, but I think you guys can watch the record videos to understand in the details. And I'm going to skip things like that. That's another way that you can do. So let me summarize it. LSTM is better than RNN, of course. But both of them still like vanishing or exploding gradient is still problematic, even for the LSTM. So the sequential data set in order to deal with the time series data set is applying the RNN or LSTM is in many cases the performance is not like as good as you expected. So it's right? The reason that I didn't explain what's the LSTM in details. So if you do the codings, this is all you need to know. Don't worry about it in the details. Don't worry about what's happening inside. You don't need to worry about it. You don't need to worry about. So only thing is just like the way you did ANN or CNNs, they had all, even we have LSTM things. Let me go back to the example that I have. Let me see. I'm going to talk about the classifications and the predictions. I have two problems. Now, these are the sequence of data set. Like I said, now we have to define the length of the sequence or windows. We have to predefine it. And it's going to be chunk of data set, sequential data set, like this. And feed into the state. And the state do have dynamic behaviors. What's the omega? We don't know. We just define the omega. I mean, we just we have to estimate the omega, the W's from data. Okay? We want to estimate what's the dynamics inside the sequential data set. And considering these time series data set, I want to do some kind of decision makings at the end. I mean, these are the LSTM structures. And chunk of data, windows, things like that. And if you do, and based on here, if you add fully connected and binary classifications, like whether this is good or not, we can do classifications. Another thing is that in many cases, for the sequential data set, in many cases, we want to know what's happening in the future, right? So what we want to do is that having the time series data set, have that, I'm going to show you. So put it that way, and it's same as regression problem. You see what I mean? So suppose we have time series data set, and I'm going to take these are the inputs and want to estimate this. And the next time I want to put it as this one is inputs and this will be the outputs. Since we already know the values in the futures, it is same as the regression problems. And at the end, take these as inputs. I want to predict, actually, but in that case, we don't have any the label data set, so that's going to be predictions. So this is the example that I have, and these are some kind of vibration signals that we have, and using that, the structures that we have, and this is the models that we implemented, and again use mean squared errors, which is you saw that in the regression problems. So in time series, prediction is same as regression. Okay. So this is the predictive values in red ones. So this is the time windows that we have the time durations estimated. But if you decide I want to predict more, that means, so let me see, I'm not sure, but say I use this amount of data to estimate this, and what we can do, I put it into input, but some of them are predictive values, which is okay. And using that, I can predict. So that's why I can predict more. But as you can see over there, now we are here, if we predict more is far away, the accuracy or performance is getting worse, which is natural. Because these are the predictions based on the predictive values, and predictive values, we add more like uncertainties, and the prediction errors is accumulated. Okay? So those are the contents that I have for like how to deal with time series data set. And I know most of you like the image as inputs, or time sequential data set as inputs, and sometimes like ANNs. And I think I cover most the common network structures, starting from the ANN, and we talk about the CNNs. Now we finish it up the sequential data set. Okay, so I will end. And from next week, I'm gonna have like kind of another topics that I'm gonna prepare for that. All right? I'm done.